Okay, good afternoon, students. So in this experiment, the experiment name is Astable Multivibrator using transistor, and the aim of this experiment is we are going to set up the Astable Multivibrator using a transistor, that is NPN transistor is there, and we are going to obtain the collector and base voltage waveform for one of the transistors. And even though we are going to determine the frequency of oscillations, and even though we are going to compare it with the theoretical value of frequency. So now let us see the main apparatuses which are required here. We are having here rich transistors, and even though you may choose the other type of transistor, no problem with that. Resistor, capacitors and power supply, and oscilloscope, that is dual trace, and even though we need the connecting wires. So one by one let us see all the components already what we have already assembled. So this is what the circuit diagram we are having here. So right now you are able to see this. We are having the couple transistors. Right now we will. I'm going to remove this connection so that you can see one by one, step by step. So let us see here. So just we removed here. So now let us remove the connecting wires. So now let us see. Just I'll keep it here. So now here we are having that this is CL100S model transistor, that is NPN, and here we are able to observe the notch is there. So this is what end of this is the emitter end, and another one is the collector, and remaining one is the base is there. So now let us put it in a breadboard. So right now I am going to insert middle of this breadboard. So just now I have inserted here, and similarly we are having the same type of transistor, that is the CL100S, and now let us see the connection what we have to do here. And even though here we are having the 1 kilo ohm of resistance, that is we are having brown, black, red, that will become 1 kilo ohm of resistance, and another couple of 1 kilo ohm of resistors we are having, that is brown, black and red, that will become 1 kilo ohm. And here this is the brown, black, orange is there, this is 10 kilo ohm. Now let us see here as per that circuit diagram. Here we are having that emitter, collector, base, and emitter, base, collector. And now just I am going to take this RB1 and RB2, RC1 and RC2. Here RB2 values, that is 10 kilo ohm. The both RB1 and RB2 are having the same values, 10 kilo ohms, and here RC1 that it is having that value 1 kilo ohm. So both are having the same values. RC1 because that resistor has been connected to the collector end, and this RB1 that resistor has been connected to the base end of the opposite transistor. And here we can see that connection. Let us see here. Let us take this RB1, that is the 10 kilo ohm. Now I am going to insert in this breadboard here. So now just I inserted both the transistors, and as well as I have taken the 1 kilo ohm of resistance, and from the collector end I am going to give this 1 kilo ohm of resistance. And here also with respect to this transistor we can see here. So here what we are having, and here also we are having that from the emitter, from the both the emitter of this transistor, that sends to the grounding, as you can see here in this circuit diagram. So this is what we can see, the grounding, that is grounding. Right now I am going to give that directly these two wires. I can give these two, no problem with that. From here to here grounding, and here, and here I have to make the cross coupling. Let us look at here. Here we are having from the base to the RB1, and from this from the T1 RB2, from T2 and RB that sends to the RB1. That's the cross coupling is there. So now I will go for the second transistor, that from the base. Here the base where I have given. Just I will remove this one. I have to give that. Okay. So now from the base that I can give to the RB1. That's all. Simply cross coupling is there, and thereafter from this RB from the transistor 1, from this base 2, I will give to the this RB2. This is 10 kilo ohm of resistance. So that's all, and this is what the cross coupling has been done in this breadboard. And here we are remaining with the other connections, and here we are having the two decade capacitance boxes. Which one is the variable that we have to choose here? We are having the 0.01 variable, 0.1 is there, 1 is there, and 0.001 is there. So in this experiment we have taken the 0.1 microfarad. So right now just I have fixed for this 1, that will become 0.1 microfarad. If you want to increase that one means, then just you have to rotate this knob, and that will become 0.1 plus 0.1. That has been multiplied to the 2. That will get the 0.2 microfarad. And now let us make the connection here. So let us from the power supply. Just I have to give the power supply. From the power supply, I will give here this end, and as we have already given from the emitter to the ground, I am going to put it here. This is the grounding, and thereafter here we are having that two decade capacitance boxes, where we have to give, just look into this circuit diagram. You can see here between the RB1, RB2 and the RC2. So RB2 and RC2 are here, as we can see here. This is the RB2, and here this is the RC2. So between this I have to give that one resistor. So that's why I can give here. You can give to the any end, there is no problem with that. Here we don't have any kind of polarities also, and here also I am going to give this another one, RC1 and the RB1. Between this I am going to give that decade capacitance box ends, both the ends. So this is RB1 and this is the RC1. So this is what we have done. So that's all. And now here we are having the output. You may take the output from this transistor, or else either this transistor or this one, T1 or T2. You will get the same output. Let us take this one. We can see here. Let us take from the emitter and the collector, we can get the output here. So now just we have connected. This is what the complete connection. It's been completed. Now I will start this dual trace oscilloscope. Okay, so now I'll make the power supply on. So now you can see that square wave, but it's reverse because the output has been reversed here. Right now I'm going to exchange these terminals so that we can get the perfect wave here output. So now we can see here, by changing this voltage we can make the variation in their amplitude, and even though by making the variation in the time per division, even though we can get the variation with respect to the time period. This is what all about the Astable Multivibrator. And even though this is what the output from one transistor, now I can shift this output from this transistor to another transistor. So you can get the same output. You can see here. Let us okay, now you can see here. So this is what we can get the outputs. So these are the outputs we can get from this another output. Okay. So if you want to make it reverse means, again you can change this one, no problem with that. So that is what the output. So again now you can get the reverse one. So this is what all about the Astable Multivibrator. Thank you. And you can see this formula. Just you have to substitute the RB values, as we know that RB1 and RB2 values, and even though we know the capacitance value, you have to substitute in this theoretical formula, and you can make the verification with respect to here. This is the tabular column C1 C2, that is 0.1 microfarad. You can change that variable, decay capacitance is there. You can change 0.1, 0.2, 0.3 like that. And even though we are having the RB value, and even though we are able to find that length of one wave, as you can see in this output of oscilloscope, and even though we are having the time base, here we are in the time per division, and you can find the period and as well as frequency. And this is what the practically you can get, and this is what theoretically, and the practical and theoretical values must be verified. Thank you.